Assalamualaikum and a very good morning to our lecturer, Madam Tan Siew Ning, and we are going to present our assignment 2. Me, I'm KAMARINA SHAHIRAH BINTI KASMAN, and my metric number is 07DKA23F1026, and my friend SHERLYN SUID with her metric number of 07DKA23F1059. In civil engineering, the hydraulic subject focuses on understanding how fluids, especially water, behave and can be controlled using the principles of fluid mechanics. It studies the pressure, flow, and energy of water to help engineers design various systems such as dams, canals, pipelines, drainage system, and irrigation networks. By applying these principles, hydraulic engineering plays a vital role in managing water resources efficiently and creating safe, sustainable solutions for water supply, flood control, and environmental protection. Question 1. Water flows half-full in a circular concrete sewer pipe with a diameter of 1.2 meter, and the discharge is Q equals to 1.8 m³ per s. The Manning's roughness coefficient is n equals to 0.013. Using Manning's equation, determine the bed slope S required to maintain this discharge under uniform flow conditions. Okay, so for this question, we are asked to find the slope S of the pipe. We are given the diameter equals to 1.2 meter, discharge equals to 1.8 m³ per s, and our Manning's n equals to 0.013. First, we need to find the radius, which is half of the diameter. So 1.2 over 2 equals to 0.6 meter. Since the pipe is flowing half full, we can find the area of flow using the formula, which is A equals to pi r square per over 2. Next, we calculate the wetted perimeter, which is, the formula is P equals to pi r. So 3.142, which is the pi, and in brackets 0.6 will equal to 1.885 meter. Now we find the hydraulic radius R, which is A over P, 0.5654 over 1885. It will give us 0.300 meter. Next, we are going to use the Manning's equation to find the slope. We are going to use this formula, which is Q equals to AR 2 over 3 power and S power 1 over 2 over N. Substitute all non-values, and we rearrange to make S the subject. And then now we'll have 0.013 times 1.8 equals to the others, which is 0.5654 in brackets 0.3 power 2 over 3 and S 1 over 2. We are going to do the equation. We will solve it until we have S power 1 over 2 equals to 0.0334 over 0.2834 equals to 0.0923. Finally, square both sides, because we want to find our subject, which is our slope, the S. By squaring both sides, our slope will be 0.0085. So, the slope required for the pipe to discharge 1.8 cubic meters per second is 0.0085, based on Manning's formula and the given parameters.
So I will continue for the question 2, the best hydraulic section of trapezoidal channel. For question 2, we are required to calculate the discharge denoted as Q for a trapezoidal channel using Manning's equation. The given data are Manning's coefficient N equals 0.012, bottom width B equal 5 meter, channel slope S equals 0.0005, and the side slope, which is horizontal, vertical, 2/3. Step 1. The formula for discharge using Manning's equation is Q equal 1 per M AR power of 2/3 S power of 1 per 2, where A is the cross-sectional area of flow, R is the hydraulic radius, which equals A per P, P is the weighted perimeter, and S is the slope of the channel. Okay, for a trapezoidal channel, the area is calculated as dy plus zy power of 2. The weighted perimeter is b plus 2y square root 1 plus z power of 2. Next, substitute both a and p into the Manning's equations. Since r equal a per p, the equation becomes 1 per 0.012 a multiple a per p power of 2 per 3 multiple 0.0005 power of 1 per 2. From the question, the target discharge is Q equal 10 m cube per s, where we then rearrange the formula to find y, the flow depth. By trial and error, different values of y are tested to make Q equal to 10. The calculations are tabulated as shown. The table on the right shows several values of y and the corresponding a and r. We calculated q for each depth using q equal 1 per 0.012, ar power of 2 per 3 multiple 0.0005 power of 1 per 2. After several iterations, the discharge q reached approximately 10 cube per s when y equal 1.07807. Therefore, the normal depth y for this channel is approximately 1.07807, which gives a discharge value of 10 m cube per s. Thank you. Question 2b. Okay, this question is about finding the normal depth of flow in a channel using Manning's equation. So, the area of flow A is given by A equal by plus zy power of 2, P equal b plus 2y square root 1 plus z power of 2, and R is A per P. We substitute this into the Manning equation and solve for y, which is the normal depth. After doing the calculation step by step, we get y equal 4.68 meters. That means the normal depth of flow in this trapezoidal channel is 4.68 meters. So now I will continue for the question 3, which involves analyzing the specific energy, the critical depth and alternative flow depths. Location of flow is subcritical or supercritical, minimum value of the specific energy depth, and the last one is critical velocity. So, the given data V equal 9.5 m per s, flow depth Y2 equal 1.2 m. So, the specific energy, the formula for specific energy is E equal Y plus V power of 2 over 2G. So, we got E. The specific energy of flow is 5.7999 meters. The next one is critical depth YC. The formula is Q equal YV. We got 11.4 m power of 2 per s. Next, we find the critical depth YC equal Q power of 2 over G power of 1 per 3. So we got YC 2.3662 meters. Next, the specific energy equation in terms of Y is Y plus 6.6239 Y power of negative 2. Okay, the next one is Prot number. We can use the formula V over square root GY2. So, from my observations, uh, Prot number bigger than 1. That means the location of flow is supercritical. Okay, I will continue for the question D, minimum value of the specific energy path. The formula is E min equal 3 over 2 YC. So we got 3.5493 meters. And the last one is critical velocity. We substitute the value into the formula Vc equal square root GYC and we got 4.8179. So after got all of the answer, we draw the graph. Since Y smaller than YC, the flow is supercritical.
Question 4. So for this question, we need to find 4 things. The depth after the jump, and then the energy loss, the power loss, and finally the type of jump. We are given width of channel 3 meters, flow rate equals to 5.6 cubic meter per second, and our slope is 0.0005, and our mannings will be 0.025. First, this is a rectangular channel. So the area is using formula of A equals B times Y, which is 3Y. And using the P formula, which is P equals to 2Y plus 3, and then we use Manning equation, which is Q equals to AR power 2 over 3 and S power 1 over 2 over N. We substitute all the values into the formula. From this equation, we find the depth Y after the jump. After that, we can calculate the energy loss using HL equals to E first minus E second. Finally, to identify the type of hydraulic jump, we look at the froth number. If the froth number is high, the jump will be strong, and if it's low, the jump will be weak. So basically, we use Manning's equation to find the depth, then find the energy and power loss, and finally determine what type of jump it is. So continuing from the previous part, we substitute all the known values into Manning's equation. We have 5.6 equals to 3y times 3y over 2y plus 3 power 2 over 3 times square root 0.0003 over 0.025. This equation helps us find the depth y. Since it's a bit complex to solve directly, we use the try and error method by assuming different values of y. In the table, we try several values like 2.41, 2.42, 2.43, and so on. And we find that when y is equals to 2.241 meters, the calculated discharge is the closest will be equal to 2.241 meters. Next, we find the critical depth YC using this formula, which is YC equals to Q square over Q over G, which is gravity, and the power of 1 over 3. And then we are going to use Q, small q, as the subject, and we'll have Q over G, which is 5.6 over 3 will equal to 1.867. So our YC will be 0.708 meters. Then we calculate the velocity using Q equals to A times V. Next, we find the Froude number. So next we are going to find energy loss. So we are going to use the formula of EL equals to y second minus y first cubic over 4 times y second times y first. So the value will be as we substitutes in them, and we'll have 7.8151. And that's the answer for energy loss. Next, we are going to find power loss by using the formula of P equals to rho Q G E L. So we substitute the values into the formula, which is 1000 for rho. The Q is 5.6. The gravity will be 9.81, and our EL is 7.8151. And we'll have the answer of 429.33. The last one we'll have to calculate and find the type of jump for this question. So we are going to use the formula of Q equals to AV. A is 3y, which is the area. So now we are going to substitute the value. We have Q, so Q is 5.6, which equal to 3 in brackets of 0.1336, and our velocity V1. So 5.6 will equal to 0.4008 V. Now we want to make the V, our velocity, as the subject. So 5.6 over 0.4008, and we'll have 13.972 as the answer. Now we are going to use the Froude formula, which is V over Y times G for and the power of 1 over 2, and we'll have the answer of 13.972 over 0.1336 times 9.81 in the power of 1 over 2, and we'll have the answer of 13.205, and the type of jump is strong jump. That's all.
Ethical consideration in terms of environmental impact. When carrying out any water-related engineering project, it's important to consider the environmental impact. Change in water flow, like building dams or modifying channels, can harm ecosystems, reduce biodiversity, and affect fish migration and riverbank vegetation. As engineers, we have an ethical duty to minimize these effects by conducting environmental assessment and applying mitigation measures before construction. Using sustainable design such as fish ladders and maintaining environmental flow helps protect natural habitats. In short, We must ensure that our projects support human progress without causing environmental damage. The next one is public safety. Public safety is one of the most important ethical responsibilities in water-related engineering. Any project that changes natural water system can create risks such as flooding, structural failure, or contamination. Engineers must design systems that are safe, reliable, and resilient even under extreme conditions. Regular inspection, yearly warning systems, and proper maintenance should always be prioritized over cost or deadlines. It's also our ethical duty to be transparent and inform communities about possible risks. In short, protecting public safety is not just a professional requirement, it's a moral responsibility.
The next ethical consideration will be community involvement. Involving the community in water resource projects is essential for ethical and effective planning and implementation. Local communities are often the most affected by changes in water management but frequently lack a voice in decision making. Engaging them through public consultations, surveys, and participatory meetings ensures that their concerns, traditional knowledge, and cultural values are respected. This involvement not only provides valuable insights into local environmental conditions and social needs, but also promotes fairness, transparency, and trust between project developers and the people they serve. When communities feel heard, they are more likely to support and cooperate with the project, while ignoring their input can lead to conflicts and long-term harm. Therefore, meaningful community participation is a moral obligation that aligns development with both human and environmental well-being.